Hello, and welcome back to the quiet cosmos. Tonight's walk never leaves the ground you already know. A bedroom, a staircase, a kitchen floor, and the quiet truth sitting underneath every one of them. The clock on your ceiling and the clock on your floor do not keep the same time. Not by feeling, not by any sense you could ever trust, but by measurement, real and repeatable. Downstairs runs a little behind upstairs, every hour of every day. And by the end of this walk, that small, exact difference will have carried us from a single room all the way out to the moon and Mars. Before the first stop, one small request. If a slow walk from a bedroom floor to the edge of the inhabited solar system, told through nothing stranger than ordinary clocks, sounds like good company for a quiet night, a quiet like or a tap on subscribe helps this channel reach more of the people already searching for exactly this kind of unhurried science. It costs nothing, takes only a moment, and it is the only thing asked of anyone tonight. Picture the room you are lying in right now. Nothing more exotic than that. The floor beneath the bed and the ceiling above it do not hold the same time. Not almost the same. Not close enough to ignore for any measurement science has yet made. Two different times, quietly running side by side in the space between your feet and the top of your head. It has been true of that room since the day it was built. It is simply true of the room itself, the way a wall is true, or a window. A clock set on the floor and a clock set on the shelf above it are not disagreeing by accident, and neither one has drifted or gone wrong. Each is doing exactly what a clock does in the place where it happens to sit, and the two places are not, strictly speaking, the same place at all. None of this is a thought experiment, and none of it is a clever argument worked out only on paper. Physicists have measured the gap between a lower clock and a higher one directly, with real instruments, more than once, in more than one country, using different kinds of clocks, built by different teams who did not know what the others would find. The results agreed. A century ago, the difference was too small for any device on Earth to catch. Smaller than the wobble in the best available clock of the day. That has changed. Today's finest clocks are steady enough to catch a shift you could never feel, never hear, never notice by any normal means, yet write down as a definite, repeatable number. Nothing in the measurement leans on guesswork. Each attempt lands close to the one before it, and each new attempt, with a slightly better clock, narrows the number rather than throwing it into question. What changes here is never the clock. Take two identical clocks, built in the same factory, on the same day, from the same batch of parts, so alike that no engineer could tell them apart by looking. Set one on the floor of a room and carry the other up onto a shelf above it, no farther than an arm's reach away. Leave them both alone, ticking away, disturbed by nothing. Come back later, compare their readings side by side, and they no longer agree. The clock that sat higher has gained a little on the one that sat lower. A gap too small to see on either dial, but entirely real once the numbers are set beside each other. Nothing about either clock broke, slipped, or wore unevenly, and neither one is the faulty twin. The parts, the craftsmanship, the calibration, all identical. Only the shelf and the floor are different, and that alone is enough to pull two perfect twins apart. Say the rule once, plainly, both ends in a single breath. A clock kept near the ceiling runs a little faster than a clock kept near the floor. And a clock kept near the floor runs a little slower than a clock kept near the ceiling. That is the whole shape of it. And every other case is only this same sentence measured in 100 different rooms, houses, mountains, and orbits. Higher always gains, and lower always falls behind. It does not matter what the clock is made of, whether it counts with gears, quartz, or the vibration of an atom. The direction never once reverses in any experiment anyone has ever run. Nor does it matter what color the walls are painted, or whether the room is warm or cold, loud or silent. Only the height enters into it. Once that single direction is fixed in mind, everything left to come is simply watching how large or how small that gap can grow. From a single shelf to an entire solar system, and never watching it point the other way. What decides the size of that gap is not how hard something pulls, but how deep a well you happen to be sitting in. Those sound like the same idea, and for a room, a house, or a mountain, they very nearly are. But they are not the same thing, and the difference will matter further on, in a way that seems to break the pattern. Picture gravity not as a hand pushing down, but as a dip in the ground, a shallow bowl around anything with enough mass to matter, deeper wherever the mass is greater or closer. How steeply the wall of that bowl slopes tells you how hard something is pulled at any one spot. How deep the bowl runs beneath you tells you something else. How much your clock falls behind one sitting up on the rim. A gentle slope and a deep bowl can sit in the very same place. Hold on to that distinction. It will explain, further ahead, why the very center of a planet, where nothing pulls at all, still keeps the slowest clock anywhere on it. Put a number on all this, and the size of it turns almost comically small. For every meter of height, the difference in pace comes to about 1 part in 10 to the 16th. Write that out in full, and it becomes a 1 followed by 16 zeros sitting under it. A fraction so thin that no scale, no stopwatch, no wristwatch anywhere in an ordinary home could ever hope to catch it. Stack every timepiece in your house, from the oven clock to the one on the wall, and not a single one carries anywhere near the steadiness needed to notice a shift that small across a single meter. It sits far below the reach of everyday engineering, in a realm reserved for laboratories built for nothing else. And yet the number is not zero. It never rounds down to nothing, no matter how small it looks written out. That distinction, tiny but real, holds at every size, carried over greater heights, longer stretches of time, and far more patient clocks than anything sitting on a kitchen counter. Numbers like that mean little until they are carried into a life actually lived. Stretch that single meter of height across an ordinary human lifetime, roughly 79 years from cradle to old age, and the total comes to about 1/4 of a microsecond. 1/4 of a millionth of a second, gathered patiently, meter by meter, day after day, for the whole length of a life. No wristwatch could show it, no calendar would ever record it, and no one living through those years would ever feel the difference build. It simply accumulates, quietly, in the background of everyday existence, the way dust settles on a shelf nobody dusts. A quarter of a microsecond will not shift a single plan, appointment, or birthday by any margin a person could act on. And yet, it is there, counted and confirmed, sitting in the gap between a life lived 1 meter higher and the very same life lived 1 meter lower, patient and small and entirely real. Here is the part easy to miss. This difference never wobbles back and forth, never averages itself out over a day or a season. A clock kept higher does not gain for a while and then lose the gain back later. As long as it stays at that height, the gap only grows, one thin sliver added after another in the same direction without pause. Move the clock and the rate of gathering changes with it, faster higher up, slower lower down. But the running total never resets to zero on its own. It behaves less like a wobble in a poorly built instrument and more like simple interest on a very small, very patient account. Nothing dramatic happens in any single hour, yet the balance never goes back to where it started. Leave 2 clocks apart for a year, and the year's worth of difference is still there at the end of it, fully intact, waiting to be read off the 2 dials the moment anyone bothers to compare them side by side. No one has ever felt this happening to them, and no one ever will. Sit in the room, stand on the ridge, lie flat on the floor of the deepest cave anyone has dug, and your own second always feels like exactly 1 second. No faster, no slower, no different from any other second you have ever counted. There is no internal sense that could catch the gap from where you are standing, because from where you are standing, there is nothing to compare yourself against. Catching it takes 2 things, always. A second clock, kept somewhere else, and a careful reading of both dials laid side by side afterward. Without that second clock, elsewhere, the whole effect is simply invisible, hidden behind the plain truth that every observer, in every place, always finds their own clock running perfectly normally. The strangeness only appears once 2 records meet. Until then, it waits in the numbers, unnoticed by anyone actually living through the time being measured. So begin again with the room you started in. Only look at it differently now. It was never one room keeping one time. It was a short column of space, floor to ceiling. And inside that column sat as many slightly different times as there were heights to hold them. One for the bed, one for the lamp on the desk, one for the crown of a doorway, each ticking along at its own small private pace. None of them argue. None of them need correcting. A room is simply taller than it is uniform. And time depends on exactly where within that height you happen to be standing, sitting, or lying down. Every staircase in an ordinary house carries this same small experiment without anyone asking it to. Walk down to the kitchen in the morning, and your clock, carried along with you, eases very slightly into a slower pace for the length of that descent. Climb back up to bed at night, and it eases back the other way, very slightly faster for the length of that climb. Neither shift could ever be felt, seen, or timed by any device smaller than a laboratory's best equipment. Yet both happen every single day to everyone who has ever used a staircase. Down and up and down, morning after morning. The body carries its clock through a narrow column of changing pace without ever noticing the crossing. No alarm goes off. No sensation marks the moment the floor gives way to the stairs. The whole exchange is built into the architecture of a two-story house, as easy to live a lifetime beside as it is to never once suspect it is there. A bedroom on the top floor and a bedroom in the basement of the very same house are not strictly aging at the same rate. A body kept mostly on the higher floor spends its years a hair's breadth further along than the very same body would have spent them a level or two below ground, night after night, year after year, in the same house, under the same roof. The gap is nowhere close to anything a lifespan could register. It is a matter of a fraction so small that no birthday would ever arrive early or late, because of which floor a person favored. Still, the two rooms are not interchangeable in this one narrow sense. A house with several stories is, height for height, a small stack of very slightly different clocks, wearing the same address, answering to the same front door, and keeping their own separate pace behind it. Nobody chooses a bedroom for this reason, but the difference sits there regardless, patient and real. Take that same idea and stretch it up through an entire high-rise, and one plain rule falls out of it. In any tall building, the slowest clock in the whole structure sits on the ground floor. Every story above it runs a little ahead, and the very top floor runs furthest ahead of all, while the lobby, the place everyone passes through without a second thought, quietly holds the oldest, slowest time in the whole address. Nobody built it to work this way. No architect drew a line for it, and no engineer signed off on a plan for it. Yet it is true of every tower ever raised, from a modest block of flats to the tallest towers on the planet. Doormen, delivery workers, anyone who spends their working hours near the entrance are, height for height, living through the building's slowest hours, while the residents on the upper floors live through its fastest ones, all inside walls that share a single front door and a single postal address. The Burj Khalifa in Dubai carries this rule to its most extreme address on Earth. From lobby to the very top of its spire runs 828 meters, and across that height, the tip of that spire gains on the ground floor by roughly 3 microseconds every year. 3 millionths of a second, gathering steadily at the very top of the tallest building anyone has raised, while the base of the same structure sits 3 microseconds further behind with each year that passes. Nobody who has ever ridden its lifts has felt so much as a flicker of it. No resident on the upper floors ages visibly faster than a neighbor near the ground, and no lease has ever been priced by the microsecond. Even so, if a clock accurate enough were carried to the top and left there for a year, then brought back down and compared against a twin that never left the lobby, the gap would be there in the readout, small, exact, and entirely real, written into the tower by its own height. A lift ride is, in its own small way, a short trip into a different pace of time and back again. Step in at the ground floor, rise 60, 80, 100 meters in under a minute, and for that brief climb your clock runs marginally faster than it would have running errands at street level. Step back out at the bottom a few minutes later, and the pace settles back to exactly what it was before you left. The whole excursion, up and down, leaves behind a difference too small for any wristwatch to register, smaller even than the difference between 2 floors of an ordinary house held for a whole year. Still, the shape of it is the same shape as everywhere else. Height changes pace, and pace changes back the moment the height is undone. A lift is simply the fastest way anyone travels through that changing pace, dozens of times a week, without a single passenger ever noticing the crossing. Even something as small as standing up from a chair changes the shape of this a little. Sitting, the distance between the crown of the head and the soles of the feet shortens by the length of the folded legs. Standing, that same distance stretches back out to its full height. Since the size of the gap between 2 points depends on exactly how far apart those 2 points sit, a standing body holds a slightly larger internal spread of pace than the very same body curled into a chair. Lie flat on a bed, and the spread narrows again, closer to nothing, head and feet nearly level with one another for as long as the position holds. None of this ever needs a decision. Nobody stands up in the morning thinking about the shape of their own internal clock, and nobody needs to. The body simply carries this changing little spread with it through every posture of a typical day, compressing and stretching without any effort or awareness at all. Carried far enough, that same spread between head and feet becomes an actual, if vanishingly small, difference in age. The head ages a little faster than the feet, simply because it sits a little higher for almost every hour of an ordinary life, standing, sitting, or walking. Across a lifetime of roughly 79 years, the running gap comes to somewhere around half a microsecond, a number too small to matter to anyone's birth certificate, but large enough for a sufficiently careful instrument to catch. No one part of the body is favored for this. It is only a matter of which part sits highest, hour after hour, for decades on end. A tall person carries a slightly larger version of this same gap than a short one, purely as a matter of everyday arithmetic. And it stays a quiet detail about the body, rather than the centerpiece of the effect itself. Put plainly, this means a human body holds more than one time at once, and it always has, long before anyone thought to measure it. The scalp runs its own hour, marginally ahead of the one kept by the ankles, and every point in between keeps some hour of its own, nested between the two. None of these small hours ever needed reconciling before now. The body simply carried on, whole and undivided in every practical sense, while these tiny internal differences sat underneath, unnoticed and unfelt. A heartbeat does not check which hour a given cell is keeping. Growth, healing, memory, none of it waits for internal agreement, because the differences involved are so far beneath the threshold of anything biology could ever register. What changes is only the description, not the body itself. Measured carefully enough, a single person looks less like one clock and more like a tall, narrow stack of extremely similar ones, all reading nearly, but never perfectly, the same hour. It would be wrong to call this a paradox, and the point is worth stating plainly. A head does not pull away from a pair of shoulders, and an ankle never falls out of step with the knee above it. The whole body stays exactly as connected and as whole as it has always been. What separates the pace of the scalp from the pace of the ankle is a number so far beneath anything biology could notice, that no organ, no nerve, no cell division has ever answered to it. Bones do not creak out of sync. Blood does not arrive early at one end and late at the other. The gap exists only on paper, in the readout of instruments built for nothing but catching gaps this small. And even there, it shows up only after very careful, very patient counting. A body remains for every purpose that matters to the person living inside it, entirely and comfortably, one thing. The day itself, from the moment of getting up to the moment of lying back down, is a long walk through dozens of tiny changes in pace. Down a flight of stairs, up in a lift, standing at a counter, sitting at a table, climbing back into bed at the top of the house or the bottom of it. None of these changes announce themselves. None of them need to. A day spent moving through an ordinary building is also, without any fanfare, a day spent moving through a small, private landscape of slightly different times. One for every height a body passes through, on the way from morning to night. Step outside the house, and the same pattern widens into a whole landscape. A clock left in a valley, and a clock carried up onto the ridge above it, under the same sky, in the same weather, sharing the same air, do not keep the same pace. The ridge runs ahead. The valley falls behind. The local climate, the soil and the view have no say in it. Only the difference in height between the valley floor and the crest above it decides which clock gets there first. A shepherd's cottage down in the hollow and a lookout hut perched on the rise above it are separated by exactly this, a difference measured in altitude and nothing else. Fog might fill the valley for a week, while the ridge sits in clear sun, or the reverse, and none of it matters to the clocks at all, since weather comes and goes. The gap in pace, set purely by height, stays fixed for as long as the two places stay where they are. Take that same valley and ridge to their most extreme scale on this planet, and the gap grows into something worth naming. The summit of Everest, 8,848 meters above sea level, runs ahead of a clock left at the shore by around 30 microseconds every year. A gap built entirely from height and nothing else. 30 millionths of a second, collected at the highest ground anyone can stand on. And the coastline falls 30 microseconds behind over the same year, every year, without ever catching up. Climbers who have reached that summit carried their own bodies, unknowingly, into the fastest hour available anywhere on the surface of this planet, if only for the short time spent standing there before the descent. No expedition has ever measured it directly. The number comes from calculation, not from a clock actually hauled to the top and back. Still, the arithmetic behind it is the same arithmetic checked again and again at far gentler heights. And there is no reason to expect the summit to answer to any different rule. Between the highest and the lowest addresses where people actually live, the gap becomes large enough to write down with real confidence. La Rinconada, a mining town in Peru, and the highest permanent settlement on the planet, sits roughly 5,530 meters above the shore of the Dead Sea, the lowest patch of dry land anywhere people call home. Carry that difference across a typical lifetime, and the running total comes to about 1.5 milliseconds. Small by the standard of a heartbeat, but no longer small by the standard of a bedroom or a staircase. A person born and raised at that Peruvian altitude will, by the time old age arrives, have spent a fraction of a second more than a person who lived out the same span of years beside the Dead Sea shore. Neither life runs faster in any way either person could feel. The difference sits entirely in the readout of a clock precise enough to hold a whole lifetime's worth of altitude in its memory. Ordinary cities carry a milder version of the very same arithmetic. Denver, built across roughly 1,600 meters of elevation, runs ahead of a city sitting at sea level by around 5.5 microseconds every year, simply by virtue of where it stands. Nobody who lives there notices a thing. Buses run on the same schedules as anywhere else, kettles boil in the same few minutes, and birthdays land on exactly the date the calendar says they should. All the same, a resident of that city who never once leaves it will, decade after decade, be living out a life that runs microseconds ahead of an identical life lived at the coast, purely as a consequence of the altitude written into the address. Cities at lower elevation carry the opposite half of the same arithmetic, falling that same small amount behind. None of it shows up on a utility bill or a birth certificate. It shows up only where anyone has bothered to build an instrument steady enough to catch it. Observatories built on mountain tops and laboratories set up in high-altitude research stations carry this as an unadvertised feature of the job. Astronomers who work at such sites, chasing clear air and thin atmosphere for the sake of sharper images, are also, without any of them asking for it, living out their working hours at a pace fractionally faster than colleagues stationed down in the lowland cities below. None of it changes how quickly a shift ends or how long a coffee break lasts by any measure a person could use. The effect belongs entirely to instruments built for exactly this kind of catching, not to ordinary experience. Even so, it is a strange thing to know about a particular career. Choose research at altitude, and the choice of workplace becomes, quite literally, a choice about which pace of time a person spends their working years inside. Nobody lists it among the perks of the posting, and yet, in a very small and very real sense, it belongs there. Long-haul flight crews collect a strange, unspendable little bonus from this same rule. One built up hour by hour over a career spent mostly at altitude. Every flight carries them for many hours at a stretch, far above sea level, far above the pace kept by anyone standing on the ground below. And across a working lifetime, those hours add up into a running gain measured in a few tens of microseconds. No airline pays it out. No pension recognizes it. It cannot be spent, saved, exchanged, or handed down to anyone else, and no crew member has ever noticed it directly, since the sensation of a faster clock does not exist for the person carrying it. By the strict arithmetic of the thing, a career spent largely at cruising altitude leaves a pilot or a cabin crew member very slightly further ahead in time than a colleague who spent an equal number of years working entirely at ground level. A professional advantage nobody has ever once found a way to cash in. All of this has leaned on one word, without ever once defining it: height. Height above what exactly? A mountain summit is usually measured above sea level, and sea level sounds like the simplest, most obvious baseline anyone could ask for. A flat, ordinary surface every coastline on the planet could agree on. It is not that simple. The sea itself is not a smooth ball wrapped neatly around a perfectly round Earth. It bulges here, dips there, rises against some coastlines and sinks below others, all because the planet underneath it is neither a perfect sphere nor evenly dense from place to place. Ask two surveyors on opposite sides of an ocean to agree on a single shared zero for height, and they run straight into this problem, sooner or later, no matter how carefully either one works. Before anyone can go further inward, into mines and trenches and the very center of the planet, that single quiet word, height, needs a proper definition, one every clock on Earth can actually agree on. The definition that survives this problem is called the geoid, and it is worth carrying the word forward from here. A geoid is not a shape drawn on a map. It is the particular surface wrapped irregularly around the whole planet, where gravity's pull and the planet's own spin combine to leave the well exactly as deep everywhere along it. Sea level, properly defined, is not simply where the ocean sits. It is this surface, and the ocean, left free to settle under gravity alone, happens to follow it closely almost everywhere it can reach. Wherever 2 points sit on that same geoid, at whatever distance apart, clocks kept there run at exactly the same pace as one another. No correction needed. Step off the geoid, up a mountain or down a mine shaft, and the pace shifts away from that shared baseline in a direction and by an amount that height above the geoid precisely predicts. It sounds abstract on paper. In practice, it is the one surface every clock on the planet can agree to call zero. The geoid produces one genuinely surprising result once the equator and the poles are compared directly. The equator sits farther from the center of the planet than the poles do, since the whole Earth bulges slightly outward around its middle, and greater distance from the center on its own would tend to speed a clock up. But the equator also spins faster than the poles, carried around by the planet's own rotation at nearly its widest point, and greater speed on its own would tend to slow a clock down. Neither effect wins. By a piece of arithmetic that still strikes physicists as almost too tidy, the two nearly cancel exactly, everywhere along sea level, from one coastline to any other. A clock kept at sea level near the equator and a clock kept at sea level near either pole run, for all practical purposes, at precisely the same pace, despite standing at very different distances from the center of the very same spinning planet. Height above the geoid, not raw distance from the center, remains the only thing that actually matters. So sea level, that phrase used so casually on every weather forecast and every hiking map, means something far more exact than water lapping at a shoreline. It marks the one surface, uneven and irregular as it is, where every clock on the planet, regardless of latitude, regardless of how fast the ground beneath it happens to be spinning, keeps precisely the same pace as every other clock sitting anywhere else along that same surface. Height, properly stated, always means height measured above that quiet, invisible line of agreement, not height above any particular patch of water. With a proper zero finally in hand, the direction to look is downward, below the line every clock agrees to call sea level. The shore of the Dead Sea sits more than 400 meters below that line, the lowest stretch of dry land anywhere people actually stand. And a clock kept there runs measurably slower than one kept at any typical coastline. A gap already large enough for the very best laboratory clocks to catch without difficulty. 400 meters of depth might sound modest beside a mountain nearly 9 kilometers tall. Yet the arithmetic does not care which direction the height runs. A metre below the line counts exactly as much as a metre above it, only with the sign reversed. Visitors who float on that unusually salty water are, for the length of their stay, occupying the slowest patch of time available anywhere on dry land. A detail considerably stranger than anything about the water's salt content. Nothing about the shore looks different from any other beach. The slowness sits entirely in numbers no eye could ever confirm on its own. Mines dig that same downward story, much deeper than any beach ever could. A shaft sunk 4 kilometers into the crust, close to the depth of the deepest mines anyone has ever worked, holds a clock running about 14 microseconds behind the surface above it every year. The slowest working pace any employed person keeps anywhere on the job. Miners who spend their careers at such depths are, by this strict and narrow measure, aging very slightly slower than colleagues who work at the surface. Though nothing about the shift feels like anything at all from the inside. No heaviness, no fatigue, no sign a body could ever register on its own. Ventilation, heat, and pressure at that depth are difficult enough problems without adding a clock to the list of things that need managing. And if a sufficiently careful timepiece were lowered down that shaft and left running for a year, then hauled back up and compared, 14 microseconds of quiet difference would be sitting there in the numbers, the deepest ordinary workplace on the planet, keeping the slowest hour. Go past any mine still worked by hand, and the deepest point anywhere on Earth's surface sits not on land at all, but at the bottom of the sea. The floor of the Mariana Trench lies roughly 10,935 meters below sea level, and a clock lowered to sit there would fall behind the ocean surface above it by around 38 microseconds every year, the largest such gap found anywhere on the planet's own surface. No permanent settlement has ever occupied that depth, and only a handful of piloted descents have ever reached it at all, brief visits measured in hours rather than years. The arithmetic runs exactly as it does everywhere else. Depth below the shared surface of sea level slows a clock down by an amount height alone can predict, whether or not anyone is present to feel it. Sunlight never reaches that floor. Pressure there could crush almost anything built for the surface, and underneath all of that crushing dark sits the single, slowest patch of time found anywhere across the entire outer shell of the planet. Now comes the strange turn. Keep going down, past the trench floor, and into the solid rock beneath it, and the pull of gravity itself begins to weaken rather than strengthen. Stand on the surface, and gravity pulls hardest of all. Descend into the crust and mantle, and progressively less of the planet's mass sits below your feet, pulling you onward, while more of it now sits above and around you, pulling in every other direction as well. By the ordinary logic of weight and pull, a place where gravity weakens should be a gentler place, one where the pace of time drifts back toward normal. It is not. Every meter carried downward past that point continues to fall further behind sea level in pace, exactly as before, even while the pull itself measurably eases. That contradiction is real, checked, and entirely resolvable once the difference between how strongly gravity pulls and how deep the well actually runs is finally taken seriously. The explanation held back from the very first room we visited finally has somewhere to land. What decides the pace of a clock was never how hard gravity pulls at that exact spot. It was always how deep the well runs beneath it. Near the surface, those two things happen to move together, so closely that nobody would ever notice a difference between them without looking very carefully. Which is why the simple version of the rule works perfectly well for a house, a mountain, or a mine. Inside the planet, they finally come apart. The wall of the well flattens out, gentler and gentler the further down you travel, while the well itself keeps growing deeper the whole way to the middle. Depth wins the argument every time, wall steepness or not. That single distinction, quiet and easy to miss on a first pass, is the only thing standing between a rule that makes sense and a rule that looks broken. Carry that logic all the way down to the exact center of the Earth, and the pull of gravity does not just weaken, it vanishes completely. At the very middle, mass surrounds every direction in perfectly equal measure, pulling outward as strongly as it pulls inward, upward as strongly as downward, and the result cancels to nothing at all. A marble set precisely there would simply sit motionless, tugged by nothing, floating in perfect equilibrium at the heart of an entire planet's worth of rock and metal. And yet that same exact point, where gravity has nothing left to pull with, holds the deepest well on the entire planet. And, by the logic already laid out, the single slowest clock anywhere within it. No pull whatsoever, and still the single slowest possible pace on the whole planet. The cleanest demonstration anywhere on Earth that pull and pace were never quite the same question, however alike the two look from any ordinary height. From there, the conclusion follows on its own, plainly and without any further argument needed. The center of the Earth, then, is younger than its own crust. Every year that passes, the middle of the planet falls a little further behind the rock under our feet, quietly, at the very bottom of the deepest well anywhere on this world. Nothing separates the two physically. The whole planet is one continuous body of rock and metal, seamlessly joined from crust to core. Only their pace of time differs, held apart by how deep into that well each particular layer sits. The crust we stand on is, in this one narrow and precise sense, the oldest part of the entire planet. Put an actual number on that difference, and it comes to something genuinely strange for a planet 4.5 billion years old. The core sits about 2.5 years younger than the crust above it, gathered patiently across the entire lifetime of the planet. A simple calculation, treating the Earth as an evenly packed ball of uniform material throughout, gives a smaller figure, closer to 1.5 years. The real planet is not built that evenly. Its core is far denser than its outer layers, packed tightly with iron and nickel under crushing pressure. And that extra concentration of mass deepens the well at the center, far beyond what a uniform sphere would produce, pushing the true figure higher, up toward 2.5 years. 2.5 years, tucked away at the very heart of a 4.5 billion-year-old world, entirely real and entirely unfelt by anything or anyone. No rock down there marks a birthday. The number exists only in careful calculation, checked against exactly how the planet's mass is actually distributed, rather than how a textbook sphere might assume it to be. That 2.5-year figure carries its own small history of getting the arithmetic wrong before finally getting it right. Richard Feynman, working the same basic idea through in his own physics lectures decades earlier, arrived at an estimate of only a day or two of difference between core and crust, a number that felt roughly reasonable at the time, given the tools then available. He was off by a factor of hundreds. Nobody caught the error for a very long stretch, in part because nobody had strong reason to revisit a calculation that looked complete enough on its own terms. It was not properly corrected until 2016, when a fuller accounting of the planet's actual density, layer by layer, finally replaced the earlier estimate with the far larger figure that stands today. A careful physicist, working from good physics and reasonable assumptions, can still land on the wrong number by nearly 3 orders of magnitude when a detail as ordinary as density gets simplified away too early. The deepest place any human being could ever imagine reaching, the very center of this planet, holds the youngest hour anywhere within it. Younger than the crust, younger than the mantle, younger than every rock a person will ever stand on. Nobody will ever visit it, and no instrument will be lowered anywhere near it. Yet, the arithmetic reaches it easily enough from the surface, layer by layer, all the way down. A planet built from rock that has sat largely undisturbed for 4.5 billion years still keeps, at its very heart, the single youngest patch of time it has ever produced, steadily ticking a few years behind everything piled up around it. Nothing about this rule was ever tied to the presence of air, weather, or ground beneath a person's feet, and it does not stop where the atmosphere happens to thin out and fade into space. Keep climbing past the last cloud, past the altitude where aircraft cruise, past the thin edge where the sky finally gives way to open dark, and the same simple direction continues exactly as before. Higher runs faster, without exception, without a ceiling, without any point where the rule quietly switches off. The well that shapes a room, a mountain, or a mine shaft does not end at the edge of the planet either. It simply keeps thinning outward, weaker and weaker with distance, the further any clock travels from the mass that built it. What has held true for a bedroom and a mountaintop stays true for anything carried far enough beyond either one. The same straight line simply keeps going outward now, first to a neighbor hovering nearby in the sky, then further still. The moon sits close enough and familiar enough to be the first stop along that outward line. A clock kept on the lunar surface gains on a clock kept on Earth by around 56 microseconds for every single Earth day that passes. A gap built from the moon sitting higher in the well around our planet, and from its own much smaller mass pulling far more gently than Earth's does. 56 millionths of a second sounds almost nothing set against a whole day, and by any human measure it is nothing at all. Left uncorrected across weeks and months of emission, though, that same small daily gap adds up into an error large enough to matter to anyone trying to keep 2 locations, one on each world, working from a single shared clock. Astronauts on the lunar surface, whenever they eventually spend real time there, will be living through days that steadily outrun the very same days back on Earth, by a margin nobody could ever feel, but nobody could safely ignore either. Faced with that steadily growing gap, timekeepers have begun drafting something that would have sounded unnecessary only a few decades ago. A separate standard of time meant specifically for the moon, distinct from the one kept on Earth. The idea is not to replace Earth time, and not to pretend the moon somehow deserves its own private universe. It is simply an acknowledgement, written into an official standard, that a different place genuinely keeps a different pace, and pretending otherwise would only build small, growing errors into every calculation carried out between the two worlds. Any future base, any future crew working for months at a stretch, needs a clock that already accounts for this gap, rather than discovering it the hard way through accumulated confusion. A separate place gets a separate time, formally, on paper, the same conclusion every measurement keeps arriving at from every possible angle. The moon itself is unchanged by the new standard. Only the bookkeeping finally catches up with what the physics has been doing all along. Mars sits further out still, and its clocks answer to the same simple arithmetic, adjusted for a different mass and a different distance from the Sun. A Martian clock runs ahead of an Earth clock by roughly 1/6 of a second every year. A modest but perfectly measurable gap built entirely from where Mars sits in its own shallower well. 1/6 of a second seems trivial, folded into a single year. And for most purposes, it is. Yet, spread across a mission lasting years rather than months, uncorrected, that same small yearly gap would eventually pull a shared schedule noticeably out of step between the two worlds. Nothing here concerns the red dust, the thin air, or the long, cold nights that make Mars itself so different from home. This is purely a matter of clock pace, decided by height and mass, and nothing about the planet's surface at all. A future mission there will carry, folded into its instruments, exactly this same small yearly correction, worked out long before anyone ever lands. Step back far enough, and even an entire planet is only another object sitting inside someone else's well. The enormous one dug by the Sun itself. Earth's own clocks fall behind a clock carried well clear of the Sun's pull, out past the reach of its gravity altogether, by around half a second every year. Simply because the whole planet, and everyone and everything on it, sits this deep inside the Sun's own gravitational bowl. Half a second a year is larger than any figure a room or a mountain can produce, and it belongs to the entire planet all at once, not to any one room, mountain or mine. Every clock on Earth, from the one on a kitchen wall to the finest laboratory standard, carries this same shared debt against a hypothetical clock parked safely outside the Sun's well. Nobody notices it, and nobody needs to, since every clock here shares exactly the same debt in the same amount. That yearly debt to the Sun is not even perfectly steady across the calendar, because Earth's own path around it is not a perfect circle. Some months carry the planet a little closer to the Sun, deeper into its well, and other months carry it a little farther out, closer to the rim. Clock pace answers to that gentle back and forth exactly as it answers to height anywhere else, tightening very slightly when the planet swings nearer the Sun, and easing very slightly when it swings away again. The whole cycle repeats once a year, a slow, barely perceptible sway built into the pace of every clock on Earth, present in the background of every single day, without a single person ever sensing it directly. No calendar marks the shift, no clock face shows it. It sits folded into the numbers, a small annual rhythm riding on top of everything else already described about height, depth, and distance from the Sun. None of the clocks in any of these places, not one on a shelf, not one at the bottom of a mine, not one carried to the Moon or to Mars, is broken, mistaken, or in need of any repair. Each one is simply reporting the spot it stands on, faithfully, without error, without drift beyond what its own construction allows. Comparing a clock at sea level against a clock on a mountain and calling the mountain clock wrong makes no more sense than comparing a ruler in one country against a ruler in another and calling one of them the wrong length because the buildings measured happen to differ. Correctness for a clock was never a single fixed target shared by every place at once. Time was always local, answering only to the particular spot where a given clock is sitting, standing, or being carried, and to nowhere else at all. Nowhere in any of these places has any single location earned the right to be called the true or correct place to keep time, and none ever will. Across the whole of the inhabited system, room to mountain to moon to Mars, to the wide gap between planets and the sun, the total spread in pace comes only to fractions of a second across an entire year. Yet nowhere inside it does one particular address stand out as more correct than any of the others. Earth is not the reference point simply because people happen to live here. The sun is not the reference point simply because it sits at the center of the whole arrangement. Every location carries the same authority over its own local pace, no more and no less. And comparing any two of them only ever produces a difference, never a verdict about which one was right. It would be tempting to look for the one clock that settles all the others, the single reading every other instrument is only approximating, even if nobody has ever actually seen it. No such instrument exists, and it was never mislaid, hidden, or lost through carelessness at some point in history. It was simply never there to begin with, because nothing in the physics leaves room for one. Every clock, everywhere, in every well of every depth, keeps its own honest local time, and none of them defers to any other as the final word. A civilization could search every observatory on Earth and beyond, and never find that missing reading, for the entirely ordinary reason that the search itself is looking for something the universe never built. One plain rule threads through every place a clock can be set down. From the floor of an ordinary room to the peak of the tallest mountain, from the center of the planet to the moon, to Mars, to the wide gravitational well the whole system sits inside. Time is a local thing, and no two clocks at different depths in that well ever keep quite the same time as one another. Not because any of them are broken, not because measurement has failed somewhere along the chain. Height decides pace, everywhere and every place, from a bedroom to a planet, has been quietly running its own honest hour the entire time, whether or not anyone ever thought to ask. That is the rule as far as the evidence goes. Place decides pace, and nowhere keeps the master copy. Every place keeps its own quiet version of time, never quite matching its neighbor, and that alone raises an odd question nobody has answered yet. If a floor and a shelf cannot agree, and a valley and a ridge cannot agree, what exactly is a second supposed to mean? A second cannot simply be whatever a particular clock counts, because every clock counts something slightly different depending on where it sits. Somewhere a choice had to be made, a single definition strict enough to hold steady no matter which country, which building, or which shelf a clock is standing on. That choice did not come from a mountain or a valley. It came from something almost absurdly small, a single atom, chosen because it never changes, no matter who is asking. Nothing about a floor or a ceiling factors into it directly, not at first glance. And yet the shelf comes back anyway, folded into the very rule book meant to describe a second at all. An answer arrived in 1967, And it did not come from watching a shadow move or a pendulum swing. A second was redefined as 9,192,631,770 oscillations of a caesium atom. Counted oscillations of a caesium atom, counted one by one and never rounded off. That number sounds needlessly precise for something as ordinary as a second, until you remember what it replaced: a fraction of a particular year, tied to a planet that never quite keeps the same pace twice. A caesium atom does not care what year it is. Count its oscillations today, count them again in a decade, and the two counts agree to a level no calendar has ever managed. The whole idea of a second quietly changed that year, from a slice of a day into a fixed number of ticks belonging to one particular kind of atom. Nobody felt the change. Every household clock kept running exactly as it had the day before, unaware that the ruler measuring it had just been rebuilt from the ground up. Why an atom? And why this one? A pendulum stretches with heat and shrinks with cold. A spring loosens with age. Gears wear, oil thickens, and every mechanical part eventually drifts from the part beside it. An atom of caesium does none of that. It cannot be sanded down, stretched, or talked into ticking a little faster to save time. Every caesium atom, wherever it sits, is built from exactly the same particles in the same arrangement. So one atom's oscillation matches another's without any adjustment at all. That sameness is the entire point of choosing it. A committee did not pick caesium because it was rare or exotic. They picked it because it refused to have an opinion, refused to age, and refused to be different from any other atom of the same kind anywhere else on the planet. A ruler is only useful if it does not stretch, and caesium was chosen for that reason. The definition is not quite as simple as counting oscillations and stopping there. An official second only counts if the caesium atom doing the ticking is unmoving and left alone, shielded from stray fields, stray heat, and anything else that might nudge its rhythm even slightly. A jostled atom ticks a little differently from a quiet one. In the same small way, a jostled pendulum swings a little differently from a steady one. Laboratories go to considerable lengths to hold a single atom motionless, suspended and undisturbed, before they trust its count for anything official. Every stray magnetic field, every trace of surrounding heat has to be accounted for and subtracted out before the number means what it claims to mean. None of that sounds like it should matter for something as small as a second. It matters enormously, because the whole definition depends on a single atom behaving the same way every single time it is asked to tick, with nothing at all pushing it off course. There is a third condition, added only later, and it is the strangest of the three. The rulebook now has to say where the atom is sitting. For a long stretch of the 20th century, that seemed unnecessary, because no clock was accurate enough for a shelf or a valley to matter. Once clocks became good enough to notice a staircase, that silence in the rulebook stopped being harmless. Two caesium atoms, identical in every other way, will tick at slightly different rates if one sits higher than the other. And the official definition had to catch up with that or stop being trustworthy at all. So the rules now specify a height as carefully as they specify the atom itself. A second measured on a mountain and a second measured in a valley are each correct locally. but only one of them counts as the official second, and the paperwork says exactly which. Precision, carried far enough, eventually forces an address onto the definition itself. Every country that keeps an official clock has to perform the same quiet correction before that clock's count is allowed to join the wider count. Each national laboratory measures precisely how high its clocks sit above the reference surface, works out how much faster or slower that height makes them run, and subtracts the difference before reporting a single number outward. A clock sitting in a mountain valley and a clock sitting near the coast do not report their raw counts directly. Both are corrected first, down to the same shared reference, so that what finally leaves the building is comparable to everyone else's. Skip that step and the whole exercise falls apart, because two honest clocks in two honest laboratories would still disagree for no reason anyone watching could see. The correction is unglamorous paperwork, checked and rechecked, and almost nobody outside the laboratories ever hears about it. That correction, unglamorous and almost invisible, is the only reason clocks scattered across an entire planet manage to agree on anything at all. What the world actually calls the time is not a single clock anywhere. It is an average, built from several hundred atomic clocks, kept in dozens of laboratories, scattered across dozens of countries, each one reporting its corrected count to a central office that combines them into one figure nobody owns alone. No single clock, however good, is trusted completely on its own. A fault in one laboratory, a fault in one atom, simply gets outweighed by the hundreds of others reporting alongside it. The combined figure moves a little each month as new readings come in, then settles into an official record kept for exactly that purpose. Ask which country actually holds the correct time, and the honest answer is that no country does, not by itself. The time everyone agrees to use belongs to no address at all. It belongs to the average, patiently recalculated from a scattered committee of clocks that never once sit in the same room together. Skip the height correction for even one laboratory in that committee, and the whole average quietly breaks. A clock on a coastal plain and another in a high mountain city are not measuring the same thing to begin with. One genuinely runs faster than the other, for reasons that have nothing to do with either clock's quality. Average two honest numbers that were never equal in the first place, and the result is not a fair compromise. It is a mistake dressed up as a calculation. That is why the correction happens before the average, not after. Every laboratory reports what its clock would have read had it been sitting at the reference surface instead of wherever it actually stands. Only once every entry has been adjusted to the same imaginary shelf does averaging them mean anything at all. The arithmetic is ordinary. What makes it work is a physical correction most people combining numbers on paper would never think to ask for. Put those two steps together, and something strange falls out. A second, the most basic unit anyone owns, turns out to have a map folded inside its definition. You cannot state what an official second is without also stating, somewhere in the small print, a height above a particular reference surface. Take that height away, and the definition stops meaning anything precise. Leave it in, and a unit of time carries a piece of geography wherever it travels. Nobody set out to build a map into a second on purpose, and no committee ever voted for geography to matter this much to something as small as a tick. It arrived as a side effect of taking clocks seriously enough to notice a staircase, then correcting for it honestly instead of pretending the difference away. A second used to sound like the smallest, plainest thing science ever measured, indivisible and placeless. That placelessness is gone now, and has been for some years in laboratories nobody outside the field tends to visit. The best caesium fountains, the workhorses behind that whole averaged figure, hold their count to about 1 part in 10,000 million, an accuracy so fine it would lose less than a second in 100 million years. That already sounds close to the limit of what counting could ever manage. It is not the limit. Optical lattice clocks, a newer design built around atoms other than caesium, read out more than 100 times finer still, because they count oscillations of visible light itself rather than the slower microwave ticking caesium relies on. Light oscillates far faster than a microwave ever could, so counting it gives many more ticks per second to compare, and many more chances to notice the smallest disagreement. These optical clocks have not replaced caesium officially, not yet, but they read a shelf's worth of height as easily as caesium reads a valley's, and considerably more easily besides. The ruler kept getting finer, long after most people had stopped expecting it to. At that level of fineness, a clock stops being merely accurate and starts being useful in an entirely different way. Move an optical clock up by a single centimetre and it notices, cleanly, without any special trick beyond simply counting for a while and comparing the count against a twin left where it started. A centimetre is nothing to a person standing in a room. Nobody has ever felt one underfoot, and no ordinary tape measure held by hand is trusted to better than that anyway. It is not nothing to a clock built this carefully. The instrument, in a very real sense, became more precise than the shelf it happened to be sitting on, since the shelf itself is rarely leveled to better than a centimetre by anyone who built it. Engineers designing these clocks did not set out to build a height detector. They set out to build a better clock, and somewhere past a certain threshold of precision, a better clock and a height detector became exactly the same instrument. The work did not begin as a search for height. It began, decades ago, as a search for the steadiest possible tick. Something no calendar, no pendulum, and no planet could ever quite offer on its own. Committees wanted a ruler nobody had to argue about, not a device that would eventually double as a way of reading a room's own geography. What it found, almost as an afterthought, is a device sensitive enough to read the shelf it stands on as clearly as it reads the atom ticking inside it. A second, defined this carefully, no longer separates neatly from the place where it is kept, and no rewording of the rulebook is likely to change that now. Ask a good enough clock what time it is, and somewhere in the answer, whether anyone asked for it or not, sits a quiet report on how high it happens to be standing. The next question, naturally, is how anyone ever managed to catch a difference this small inside an ordinary working laboratory at all. 1959, Harvard. A stairwell tower rather than a mountain. 22.5 meters of ordinary university building, with a shaft running the height of it. Two physicists, Robert Pound and Glenn Rebka, fired gamma rays up that shaft from the bottom and set out to measure exactly what happened to them by the time they reached the top. No mountain, no aircraft, no rocket, nothing more dramatic than a stairwell most students in the building had walked past 100 times without a second look. The choice was deliberate. A tower inside a normal building could be measured, sealed, and controlled far more precisely than any mountain slope ever could. What they were chasing was a prediction stranger than the setup. That light climbing, that modest 22.5 meters, should arrive at the top carrying measurably less energy than it started with. A change nobody had ever managed to catch inside a building before. Light gives up a little of its own energy as it climbs away from anything heavy, arriving further along its path, very slightly poorer than it left. That is the plain statement behind the whole experiment, stripped of equipment and stairwells. Climbing costs something, even for light, even though light has no mass to slow down in the usual sense. The energy does not vanish. It simply shows up as a small shift in color toward the red end of the spectrum, the same direction light shifts when it is stretched rather than compressed. Nobody had measured that particular shift over a distance as small as a university stairwell before 1959. The prediction had existed for decades on paper, tucked inside equations built to describe stars and planets, and it had never once been tested somewhere as unremarkable as a 22-meter shaft between two floors. Pound and Rebka intended to close that gap on a scale small enough to fit inside one building. Restate that in terms of clocks, and it becomes a familiar claim rather than a new one. A crest of a light wave is, in effect, a tick, the smallest unit a beam of light has to offer. A source ticking a little more slowly sends out fewer crests in a given stretch of time, and whatever receives that light further away counts fewer arrivals than it would from a source ticking at the normal rate. Redder light, arriving from lower down, is simply a slower tick made visible, translated from a shift in timing into a shift in color that a detector can register directly. The experiment was never really about color for its own sake. It was a clock experiment wearing the disguise of an optics experiment, using a beam of gamma rays as the pendulum and a stairwell as the two mismatched shelves being compared. Read that way, the whole result loses its strangeness. It is an echo of every clock comparison already made, just measured in a different unit. 2010. The National Institute of Standards and Technology. 2 clocks, each built around a single trapped aluminium ion, sat side by side on a laboratory bench, ticking together as closely as any 2 clocks in the world could manage. Researchers then lifted one of the 2 clocks by 33 centimetres, about a foot of height, and left the other exactly where it had been. Nothing else about the setup changed. Same ions, same equipment, same room, same afternoon. Only the height of one bench moved by roughly the length of a dinner plate held on edge. After running the pair long enough to gather a reliable count, the 2 clocks disagreed, and the disagreement matched the predicted number closely enough to leave no reasonable doubt about the cause. 33 centimetres, a height nobody would ever notice while walking through a room, had become large enough for a well-built pair of aluminium ion clocks to read directly, cleanly, without ambiguity. 33 centimetres is nothing special as heights go. Roughly the rise of a single stair, climbed without thinking dozens of times in a single day. What made it remarkable was not the size of the step, but that a clock finally existed sensitive enough to read it at all. Carried out across 79 years instead of a laboratory afternoon, that same tiny step would add up to about 90 nanoseconds of difference between the raised clock and the one left below. A gap smaller than the time it takes a fingernail to grow by less than the width of an atom. Nobody lives beside a single step for 79 years without ever moving, so the number stays a curiosity rather than a lived experience. What it does prove is worth keeping. The effect being described here is not a rounding error invented to make a tidy story, but a measured quantity with a measured size, attached to a measured height that anyone could climb in 3 strides. In Tokyo, in 2020, instead of moving a laboratory bench, researchers built optical clocks, small and stable enough to travel. Then carried a pair of them into a working broadcasting tower, setting them 450 meters apart in height, with the tower still open for ordinary business the whole time. One clock stayed near street level. The other rode a lift up to an observation deck near the top, far from any laboratory, connected back down by a fiber link running through the building's own infrastructure. The 2 clocks compared notes continuously, reading a difference of a little over 1.5 microseconds for every year the arrangement ran, exactly in line with the height separating them. This was not a purpose-built research tower cleared out for the experiment. This was a public landmark doing its usual business, with 2 portable clocks proving a point about height between meetings, deliveries, and everything else the tower was busy doing anyway. A comparison made in 2018 went somewhere far less convenient than an office tower. One optical clock stayed in a laboratory sitting out on open ground. Another traveled to a research facility built into a mountain, roughly a kilometre higher than the first, reached only through tunnels bored straight through solid rock. The 2 sites sat in different countries, joined by a single strand of optical fibre, laid specifically to carry the comparison across the border without losing any of its precision along the way. Running a comparison over that kind of distance, through a cable rather than through open air, was itself a considerable piece of engineering, quite apart from the physics being tested. When the numbers came back, the clock inside the mountain, sitting a kilometre higher, ran faster than its counterpart out on the open ground, matching what a kilometre of extra height was expected to give. A tunnel under a mountain became just another shelf, only cut from rock instead of built from wood. 2022. Gila. The comparison shrank down to a single cloud of atoms held in one trap. No separate building, no separate bench, no journey of any kind. Researchers read a measurable difference between the top of that cloud and its bottom, across a gap of about 1 millimetre of height, thinner than a coin standing on its edge. The 2 halves of the very same small cloud, sharing the same room, the same trap, the same instant, still disagreed with each other once the reading was fine enough to notice. Nothing moved between the 2 readings, except which slice of the cloud the detector happened to be looking at. A millimetre had always been far too small a height for anyone to imagine measuring this particular effect across. By 2022, it was no longer too small, only unusually demanding. And demanding was, apparently, no longer a reason to stop trying. At a millimetre, the whole idea of treating an instrument as a single point quietly stops making sense. The top of that cloud of atoms and the bottom of it are, strictly speaking, 2 different places now, each keeping its own pace, however briefly and however slightly they disagree. A clock, once accurate enough, cannot be shrunk down any further without running into its own height as a genuine complication rather than a rounding error to ignore. Engineers building the next generation of these instruments now have to decide, quite seriously, which millimetre of their own equipment counts as the official reading point. Because a millimetre higher or lower inside the same device is no longer close enough to call identical. None of that is a failure of engineering. It is simply what happens once a ruler becomes finer than the thing it was built to measure. The device meant to measure a difference in height had, without anyone planning it, become tall enough itself to disagree with its own base. The finer the clock, the more its own size gets in the way. None of these 5 results needed a mountain, a spacecraft, or anything exotic to make its case. A stairwell in a university building, a laboratory bench lifted by the height of a dinner plate, an office tower still open for business, a tunnel bored through rock, and a single cloud of atoms barely a millimetre tall. 5 ordinary settings, each one catching the same quiet effect at a smaller scale than the setting before it. Every experiment agreed with every prediction, down to the decimal place the equipment could reach, and not one of the 5 ever produced a result that needed explaining away or setting aside. What started as a stairwell test in 1959 ended 63 years later inside a cloud of atoms too small to see without help. A difference in scale of tens of thousands to 1 between the first apparatus and the last. The distance between those 2 experiments is not really about physics changing. It is about how much finer a clock has learned to listen, and how much smaller a height it has learned to notice along the way. 1971, 2 physicists, Joseph Haffel and Richard Keating, bought aeroplane tickets, not for themselves alone, but for a set of caesium clocks, traveling as paying passengers with seats of their own. Nothing about the flights was custom-built for the experiment. These were ordinary commercial routes, the same kind anyone might book for a holiday or a business trip, with the clocks strapped in, switched on, and left to keep counting the entire way. No laboratory, no specially cleared building, no cooperation required beyond an airline willing to sell an extra seat, and a crew willing to leave the equipment alone in flight. The whole idea sounds almost too plain to matter. Fly a very good clock around the world on a normal ticket. Then compare its count against an identical clock that never left the ground. Haffler and Keating were betting that plain was exactly the right way to test a prediction that until then had only ever been checked on paper. The clocks flew 2 separate circuits, one heading east and one heading west, each with its own string of ordinary landings, layovers, and transfers along the way, exactly like any long-haul passenger making a round trip. Every stop added waiting time on the ground. Every transfer added a walk between gates. And none of it was smoothed away or corrected out of the experiment. The clocks simply kept counting through all of it, the same way a passenger's watch keeps counting through a delayed connection. Ground crews handling the clocks treated them as luggage, checked and rechecked at every stop, with nobody at any airport along the way asked to do anything unusual on their behalf. Back home, the traveling clocks sat down beside a reference clock that had spent the entire trip ticking in one place, never once leaving the ground floor of its own building. Comparing the 2 counts meant lining up months of preparation against a difference measured in a few hundred billionths of a second, a gap almost absurdly small next to the trouble taken to produce it. Both sets of traveling clocks came home reading something different from the clock that had stayed behind, and the 2 differences were not the same size, nor even the same direction. The clocks that had flown eastward came back running a little behind the stationary clock. The clocks that had flown westward came back running a little ahead of it. That split by direction was not a flaw in the experiment. It was the specific detail the prediction had insisted on beforehand, worked out on paper years before any ticket was ever booked. And it was exactly what the returning clocks showed once their counts were finally compared side by side. The measured gaps, only a few hundred nanoseconds either way, sat within the margin the calculation had allowed for, given how hard it is to pin down a jet's exact speed and height across an entire journey. A result that merely showed some difference would have been interesting. A result that showed the correct difference in the correct direction for both circuits at once was very difficult to explain away as coincidence. Two separate effects were pulling on those clocks at once, and they did not simply cancel each other out. Altitude pushed every traveling clock forward, the same gentle nudge a mountain gives a clock left sitting on its summit, because a cruising aircraft spends its whole flight well above sea level. Speed pulled the other way, slowing a moving clock relative to one left standing still, an effect with nothing to do with height at all. Add the two together, and the balance depends entirely on how fast the plane traveled and how high it climbed to get there. Numbers that differ from flight to flight and route to route. For the particular circuits Hafele and Keating chose, speed gained the upper hand on the eastward run. On the westward one, it stopped opposing altitude at all, and both effects ran the clock ahead together. Untangling which of the two effects was doing how much work took nearly as many hours of careful arithmetic as the flying itself had taken in the air. The gap between the eastward result and the westward result comes down to something even simpler sitting underneath both flights. The planet itself is already turning. A plane flying east adds its own speed on top of the ground's existing spin, while a plane flying west cancels part of that spin out, traveling briefly against the direction the surface underneath it is already moving. Two aircraft with identical cruising speeds, identical altitudes, and identical flight times can still end up with different net speeds relative to the planet's center, purely because of which direction they happen to be heading. That single detail, easy to miss and impossible to ignore once noticed, is the entire reason the eastward clocks and the westward clocks did not mirror each other, and it is a detail that has nothing whatsoever to do with the quality of either clock. The Earth's own rotation, quietly along for the ride on every flight ever taken, had to be added into one direction's ledger and subtracted from the others. None of this needs a purpose-built experiment. It happens on long flights every day. 10 hours cruising north or south at around 10 kilometers of altitude leaves a wristwatch running about 27 nanoseconds ahead of an identical watch left on the ground, the height advantage outweighing the small drag from the aircraft's own speed. Climb a little higher or fly a little slower, and the balance shifts slightly, though the overall size of the gap stays roughly the same order for any ordinary passenger jet. Nobody boarding a long-haul flight has ever noticed a watch drifting mid-journey, and nobody ever will, because the gap sits many million times smaller than anything a wrist could register. It is there nonetheless, accumulating in the overhead locker the entire flight, present in every passenger's pocket, whether or not a single one of them has ever heard of Hafele or Keating. A transatlantic crossing is, among everything else, a very small, routine repeat of an experiment first run with tickets bought on purpose in 1971. What makes the whole episode worth returning to is not the technology involved, none of which was especially exotic even in 1971. It is the ordinariness of every part of the setup. The clocks were the kind a laboratory might use on any given Tuesday. The aircraft were the kind anyone could book a seat on. The tickets were paid for at the counter like any other ticket, with nothing about the booking marked as special. No custom spacecraft, no purpose-built tunnel, no restricted facility, just clocks, seats, and a published set of commercial timetables, treated with enough care to turn a routine round trip into a controlled comparison, with every stopwatch reading, every boarding pass, and every seat number logged as carefully as any measurement taken inside a laboratory. Careful bookkeeping, not exotic equipment, is what made the whole thing count as an experiment rather than merely an unusual holiday. That plainness is, in its own way, the whole point of the story. A prediction about the whole shape of time did not need anything grander than an airport check-in desk to be tested and confirmed. Sunlight itself carries the same signature by the time it reaches a rooftop or a window ledge, arriving very slightly redder than it left, by about 2 parts in a million. That shift is nothing more exotic than a reading taken from a very great distance. The light is a clock's report, sent from a source about 150 million kilometers away, and a rooftop is simply where that particular report happens to be received and compared. Nobody needs to travel anywhere to see it. The shift is already there, inside sunlight streaming through any ordinary window, waiting for an instrument fine enough to notice a difference this small, tucked inside an otherwise unremarkable beam of daylight. The same statement was made about a stairwell in Massachusetts, about a bench in a laboratory in America, and about a tower in Tokyo, only carried across 150 million kilometers of empty space, rather than a few dozen meters inside a building. Every heavy object does the same quiet thing to light departing from near it, whether that object is a star, a planet, or a laboratory floor. The size of the effect scales with how heavy the object is and how close the light started to it. A star manages a shift measured in millionths, while a laboratory floor manages one, measured in fractions, far smaller than any instrument could ever hope to register directly. Nothing about the underlying rule changes between the two cases. Only the scale changes, stretched or shrunk, depending on how much mass is doing the pulling and how far the light has to climb before anyone measures it. Sunlight and a gamma ray inside a Harvard stairwell are, in that sense, telling exactly the same story. The gamma ray in a whisper too quiet for any instrument built before the middle of the 20th century. The sunlight loud enough for a rooftop and a bench spectrometer to catch without much trouble at all. Aircraft, laboratory benches, and sunlight itself all end up agreeing, each in its own units, each at its own scale, each without needing a single exotic ingredient to make the case. A clock with a boarding pass, a clock lifted on its bench, and a beam of daylight have each, separately, told the same quiet story about height and pace, and none of them needed a spacecraft, a specialist facility, or a single piece of equipment built only for this one purpose. Commercial airlines, university laboratories, and a morning window all turned out to be perfectly good places to catch an effect once assumed to live only in equations. None of it required disbelief, only patience, careful instruments, and enough repetition across enough settings to leave very little room for doubt. A stairwell test in Massachusetts had turned into routine laboratory business, checked again and again in buildings never designed with any of it in mind. Clocks have become accurate enough in certain laboratories to work as an altimeter in reverse. Instead of measuring height and predicting how a clock should run, researchers now measure how a clock runs and calculate the height it must be sitting at. Compare two optical clocks carefully enough. Note exactly how much faster or slower one runs relative to the other, and the height difference between them falls straight out of the arithmetic, without a single tape measure or survey stake involved anywhere in the process. It sounds like an unlikely use for a device built to count oscillations of an atom, and for most of the history of clockmaking, it would have been an unlikely use, because no clock was ever fine enough for the trick to work. In a handful of laboratories, it has simply become one more way of asking a very good clock a question and trusting the answer it gives back. For most of what has been described, the arrow of trust ran in one direction only. Height was measured first by conventional surveying, and clocks were corrected afterward to account for whatever height had already been established by the survey. That order has reversed in the most precise laboratories now working. Nothing was decided or announced when that swap happened. It arrived simply because one of the two instruments kept getting finer, decade after decade, while the other stayed roughly where it had always been. A surveyor with decades of experience would find that reversal almost bewildering. The instrument once corrected by a map is now the one correcting the map. Surveyors spent centuries improving their instruments to read height more finely, and it is a peculiar kind of progress that the finest height reading available today comes not from a theodolite or a conventional survey at all, but from two atoms, patiently compared against each other, agreeing or disagreeing by an amount too small for almost any other instrument on the planet to notice. That reversal is useful for a very practical reason. Linking the height reference used on one continent to the height reference used on another has traditionally meant stringing together an unbroken chain of ground-based measurements, survey point by survey point, sometimes across mountains, coastlines, and borders that make the chain slow and expensive to build. Errors accumulate along a chain like that, much the way rounding errors accumulate through a very long sum, growing a little with every added link, however carefully each individual measurement was taken. A pair of good enough clocks skips the chain entirely. Place one clock at a known reference point on each continent. Compare their readings over enough time to gather a reliable count. And the height gap between two reference surfaces separated by an ocean shows up in the comparison directly, without a single intermediate survey marker standing between them. Two atoms, thousands of kilometers apart, can settle an argument that used to take a chain of surveyors years to close. This kind of precision matters most in places where the change being tracked is measured in centimeters spread across decades, rather than meters spread across a single afternoon. Sea level creeping upward, groundwater draining out of an aquifer, land slowly sinking under the weight of a city built on soft ground. All three show up first as a slow drift in height, often too gradual for conventional surveying to catch cleanly against its own background noise. A clock sensitive to a single centimetre of height, left in place and compared patiently over months or years, can catch exactly that kind of drift, reading a slow sinking or a slow rise that the conventional survey might need years of repeated visits to confirm with equal confidence, if it can confirm it at all. Where the story is written in centimeters and years, rather than meters and days, a very good clock has become one of the more useful instruments available. There is a ceiling on how far this trick can be pushed, and the ceiling is not the clock. The geoid itself, the reference surface every one of these comparisons ultimately depends on, is only known to a couple of centimeters in the best surveyed places, and to 10 or 20 across much of the world. A clock this fine is, in an important sense, already better than the map it is being compared against. A very comfortable problem for an instrument to have after decades spent chasing the opposite complaint. Push the clock's precision any further, and the extra fineness has nowhere useful to go, because the map underneath it simply cannot confirm or deny a difference smaller than its own uncertainty. The limiting factor in the whole enterprise has shifted from how well a clock can count to how well anyone actually knows the shape of the planet those counts are being measured against. Which leads to an odd conclusion for anyone expecting the next great advance in timekeeping to come from better physics. The next official redefinition of the second is not really waiting on a better atom, a better laser, or a cleverer trap to hold ions steady. Optical clocks built today already outperform the geoid they are compared against, sitting on the demanding side of a limit that used to belong entirely to the clocks themselves. What the field is waiting on now is better geography, a more precisely mapped reference surface, agreed internationally, fine enough that comparing two of the best clocks in the world would no longer be limited by uncertainty in the map sitting underneath them. Committees that once worried mainly about atoms and lasers now spend a good portion of their meetings discussing surveys, sea level records, and international agreements about whose measurement of a coastline counts as authoritative. A unit built from an atom, the smallest and most fundamental thing anyone measures, is currently held back by something as unglamorous as an accurate survey of hills, oceans, and the uneven pull of the ground beneath them. A plan already exists to close that gap. International standards bodies have set out a rough timetable to redefine the second officially around the year 2030, shifting the underlying reference from a caesium atom's microwave ticking to one of several optical transitions already running in laboratories today. The change will not alter how long a second feels to anyone living through an ordinary day. It will simply swap out the atom doing the counting for one that ticks faster and disagrees with itself less. Several candidate transitions are still being compared against each other in different atoms and different laboratories before any single one is chosen to carry the whole definition forward. Before that change can be signed off, laboratories around the world have to agree, clock by clock, that their chosen optical transitions read the same value closely enough to trust, wherever on the planet each laboratory sits. The paperwork alone, corrected for height, will take most of the coming decade to finish properly. Underneath all of that paperwork sits a heavier question than any committee timetable can settle by itself. What does it actually mean for two clocks kept thousands of kilometers apart and never once placed side by side to be reading the same time at all? Comparing two clocks in the same room is straightforward. Stand them together, watch the counts, and settle any disagreement directly. Comparing two clocks separated by an ocean, each correct for its own height and its own place, asks something subtler. Because there is no single shared room for either of them to be brought into, and no way to lift one bodily across the water to check it against the other by hand. Every method used to bridge that gap, whether fiber cable, radio link, or careful calculation, is really just a more elaborate way of asking the same old question a shelf and a floor asked at the very beginning. Only now asked across a much longer distance. Distance changes the difficulty of the comparison. It never changes the question being asked. There is no paradox tucked inside any of this, however strange it can sound when said all at once. The word now has simply turned out to be a local word, true only for wherever it is spoken. And there is no single now anywhere in the universe that everyone, everywhere, could ever agree to share. A clock on a mountain and a clock in a valley are not arguing about who is right. Each is reporting its own place correctly, and being correct is a claim that only ever makes sense locally, never universally. There is no referee sitting somewhere outside the whole arrangement, ready to declare one of the two clocks the real one and the other merely mistaken. Once that idea settles, the whole subject stops sounding like a catalogue of small errors and starts sounding like something closer to the truth about what a clock has always actually been measuring. Not time in general, but time exactly here, for as long as here happens to hold it. None of these later steps overturned a single number already given. They only explained why those numbers had to come out the way they did. A caesium atom, a mountain, an aeroplane ticket, and a beam of sunlight all point toward the very same rule from very different directions, and not one of them disagrees with any of the others once height is properly accounted for. Engineers building height gauges, physicists redefining a unit, and travelers carrying an ordinary wristwatch onto a plane are, without realizing it, all leaning on the very same handful of numbers, checked in laboratories most of them will never visit. What began as an odd claim about a floor and a ceiling has, by this point, become something closer to a routine piece of engineering, checked, rechecked, and quietly folded into the definition of a second itself. One question, though, still sits underneath all of the checking and rechecking, unresolved by any single measurement on its own. Nobody has ever managed to feel any of this happening, and nobody ever will, no matter how sensitive the instrument built to catch it from the outside. From inside any single place, a second is always exactly a second, counted the same unhurried way it has always been counted, whether that place sits in a valley, on a mountain, or anywhere between the two. No amount of attention paid to your own pulse will ever reveal it, because the disagreement lives entirely between two places, never inside a single one. The disagreement only shows up in comparison, never in the lived experience of either clock or either person doing the living. That is not a flaw in the reasoning, and it is not a trick played by careful wording. The whole effect has simply always worked this way, from the very first floor and ceiling described, right through to the smallest samples any laboratory has managed to compare. Anything with height at all quietly holds more than one time inside it, whether or not anyone ever measures the difference directly. A tree holds one time at its roots and a slightly different one at its crown. A tower holds one time at its base and another at its upper floors. A person holds one time at the ankles and another at the scalp. A planet holds one time at its surface and another, slower still, buried at its center. Even a mountain range does the same, one time along its lowest foothills and another along its highest ridge, whether or not a single instrument has ever been carried up there to check. None of these examples needed a laboratory to become true. The laboratories only made the differences visible. Height is height, whether it belongs to a tree, a building, a body, or a world. And wherever height exists, more than one time exists alongside it, waiting for an instrument patient enough to notice. Take a single sequoia, tall enough to stand among the largest living things on the planet, and give it 3,000 years to grow, roughly the age some of the oldest of these trees have already reached. A crown standing close to 100 meters above the roots is nothing extraordinary for a tree like this, the tallest of them hidden in low cloud on a damp morning. Across that whole span, the crown runs ahead of the roots by only about 1 millisecond, a gap smaller than the blink of an eye and utterly unfelt by the tree itself in any way that could ever matter to it. 3,000 years of patient growth, reduced to a single thousandth of a second of disagreement between the top of the tree and the bottom of it. The tree is none the wiser for that gap. The wood does not know, the rings do not record it, and no forester has ever needed to account for it in any practical decision about the tree's care. Every one of these clocks, from a pendulum in an ordinary house to an optical lattice clock counting oscillations of light, was telling the truth the entire time. None of them was ever broken. None of them was ever wrong. And none of them, strictly speaking, ever agreed completely with any other clock standing at a different height. Said all at once, that combination sounds like a contradiction dressed up in careful language. The kind of claim that ought to collapse under its own weight. It does not collapse, because the local nature of a second is taken seriously. Every clock reports its own place correctly, and correctness, once height enters the picture, simply stops meaning identical to every other correct clock elsewhere. A whole planet's worth of clocks, all honest, all slightly different from one another, is not a flaw anyone needs to fix. It reads instead as the expected, unremarkable outcome of building very good instruments and then scattering them across a world that is not flat. None of it came as a surprise. Albert Einstein set this whole prediction down on paper in 1907, decades before any instrument existed sensitive enough to check whether it was true. He worked it out from first principles, reasoning about falling lifts and accelerating rooms rather than from any measurement available to him at the time, because no such measurement was remotely possible with the equipment of that era. The paper itself was short, almost modest, tucked among other work, and easy for a casual reader of the period to pass straight over. 52 years passed between that paper and the first experiment capable of testing the claim on solid ground. The stairwell experiment in a Massachusetts university building. For more than half a century, the idea sat in journals and lecture notes, believed by physicists who trusted the reasoning behind it, unconfirmed by anything more solid than mathematics. 52 years is a long stretch for anyone to wait for proof of something they were already fairly confident about. There is no master clock sitting anywhere on the planet keeping the one true count that every other clock secretly answers to. It was never lost, never hidden away, never broken by accident somewhere along the way. It never existed in the first place, not even before any of these particular clocks were built, because a single master clock was never something the universe was ever going to offer anyone. People sometimes imagine one anyway, tucked away in a vault somewhere, quietly keeping the real time, while everything else merely approximates it. No such vault exists. No committee has ever pretended otherwise when pressed on the question directly. And yet nothing about daily life anywhere depends on such a thing existing. Trains run, calendars agree closely enough for every practical purpose. Laboratories compare their results, and none of it required one ultimate clock standing behind the whole arrangement, keeping everyone else honest from some quiet room nobody has ever found. Trace the whole shape of this account, from where it opened to where it now stands, and one plain thread runs through every stop along the way. It began with the floor and the ceiling of a single ordinary room, then moved through a staircase, and the small disagreement carried inside a person's own height, out across a valley and the ridge above it, and onward to the one surface where every clock on the planet finally agrees. From there it went downward, into a mine shaft, into the deepest trench on the seabed, and into a planet's own solid iron center, younger than the crust sitting above it. It climbed back out again, past the moon, past Mars and out into the wider pull of the Sun itself. Then turned toward the caesium atom and the careful definition built around it. It followed that definition into a stairwell of gamma rays, a bench lifted by 33 centimetres, a single cloud of atoms, barely a millimetre tall, a set of aeroplane tickets bought for ordinary flights, and a beam of sunlight arriving very slightly red. Nothing about any of this needs to be corrected, mourned, or explained away as a flaw in how the universe was built. Time is held by place, quietly and without exception, and every place, from a shelf to a mountain to the buried center of the world, holds its own a little differently from its neighbor. That was true long before any clock existed fine enough to catch it, and it will stay true long after these instruments have been replaced by better ones still. No committee needs to step in and settle the disagreement between a floor and a ceiling. It was never a disagreement in the first place. Only two heights, a meter apart, keeping the pace each of them was handed. A room does not need to be fixed because its floor and its ceiling disagree by a fraction too small to ever notice. And nobody standing in that room has ever needed to know the number to be affected by it anyway. Nothing here was ever broken. Only quiet, only local, and only ever a matter of 1 part in 10 to the 16th for every meter of height. The account that filled this whole evening finally comes to rest, the way it always was going to. Every floor, every mountain, every atom mentioned tonight kept doing exactly what it has always quietly done, disagreeing by amounts too small for anyone lying still to ever feel. Nothing needs solving from here. No clock is waiting to be corrected. No height is waiting to be climbed. No number is waiting to be checked again before morning. If a slow evening spent comparing shelves and mountains and atoms was good company for drifting off, a quiet subscribe helps this small channel find more listeners who want exactly this kind of unhurried night. Beyond that, there is only the room settling around you, its floor and its ceiling holding 2 times too small to ever separate you from either one, while breathing slows and thoughts loosen, and the whole long comparison finally lets itself go quiet, all the way down into sleep.